Good evening, ladies and gentlemen. How are we all this evening? Good. Good to hear. Well, my name is Mark Razzie from the Public Services Office. Just want to thank you guys all for turning out tonight. Tonight's lecture will discuss the recently found 2003 UB313, formerly known as Xena, an object larger than Pluto and with an orbit at least twice as large. We'll find out the latest thoughts about the new definition of a planet and how astronomers are continuing to find larger and smaller bodies in the outskirts of our solar system. Tonight's speaker is a professor of planetary astronomy at the California Institute of Technology, where he teaches classes from Introduction to Geology to the formation of the solar system. He's a native of Huntsville, Alabama, where he grew up listening to the tests of the Saturn rockets preparing to go to the moon, which inspired him to earn his undergraduate degree in physics from Princeton University and his PhD in astronomy from the University of California at Berkeley. He and his research group spend their time searching for and studying the most distant objects in the solar system and drinking coffee. Ladies and gentlemen, Dr. Michael Brown.
You know, they always ask you to write these bios for you, so I always put in a few stupid lines to see if they actually use them, and he actually used it. This is the first time anyone's actually mentioned the drinking coffee part, but we really do actually drink a lot of coffee because this is what astronomers have to do to stay awake and do these things. The first question is, how many people are here because they're getting class credit for being here? All right, I'm going to try to make it interesting even for you guys who don't actually want to be here but are here for class credit. So no leaving. I saw who you were, so no sneaking out because I actually know your teachers and I'll tell them that you snuck out in the middle. So this talk, I have a version of this talk that's been sort of morphing as all the different goings-ons have morphed. And even today, things have changed, and I actually, the talk hasn't changed since the things today, but I'll talk about all of them. And the first one is that this title doesn't make any sense anymore. So this was last month's title. There was actually a week-long period in August where I had changed the title to be the 12th planet. I don't know if any of you, but that didn't fly for very long. So it's now officially the title is the let's see if I can remember what it is, the largest dwarf planet, which now actually even has a name. I didn't used to have the name on there because 2003 UB313 is kind of a dumb name, but as of today, it actually has a real name. Does anybody know the real name today? Eris. Okay, we'll talk about the real name. So it got the name just today. I knew it was coming soon, but I thought it was going to come out on next Monday, and I wouldn't be able to tell you guys, but I get to talk all about the name. Largest dwarf planet. It's not quite as exciting as finding the 10th planet, but I'd just like to point out, for anyone who's a little disappointed that this is the largest dwarf planet, it is the largest dwarf planet in the known universe. It's not just, there are no dwarf planets anywhere known that are larger than this. So there's a reason for all of this sort of planetary craziness that's been going on for the last month and even for the last couple of years. People have been hearing about, are these things planets or not planets? And the real reason for all of this craziness, the real fault, a lot of the email I get these days claims it's all my fault. And it's not just from my wife. It's from other people too. It's really the fault is squarely to blame on that crazy little ice ball out in the outer solar system, Pluto. If Pluto had not had a few things going on about it, we wouldn't have been in this mess. But Pluto really screwed things up back in 1930. And the way it screwed things up back in 1930 is it really should not have been found. If we hadn't found Pluto until sort of 10 or 20 years ago, then this whole mess wouldn't have happened. But Pluto, even when Pluto was first found back in 1930, it didn't really fit the pattern of the other planets. One of the reasons is because it was when people were looking for it, they were expecting to find something big. They actually had done some calculations and thought that they had shown that Neptune, the last planet, I used to say the last planet before Pluto. Now I can just say the last planet. Neptune, the last planet, was moving along in its orbit, but it looked like he was being tugged a little bit in one direction or another by something really massive out there. It turns out we now know that that's not true. That Neptune was just moving along, minding its own business the way it's supposed to. But at the time, the data weren't very good, and people thought it was being tugged along a little funny, and so they were looking for this big, massive object out there. And one of the very earliest people looking for these things was an astronomer named Pickering. Pickering was looking, actually had some people take pictures up here on Mount Wilson, and he took pictures that looked sort of like this. And he expected to find something big. If Saturn were in this picture, Saturn would be sort of this big. And in fact, Pluto's in this picture. But you can't really tell, can you? It just looks like every other star that's in this picture. And so Pickering sort of looked at these pictures from Mount Wilson and went back to the drawing board. And the real trick to finding these things in the outer solar system really came from Clyde Tombaugh in 1930. He had been hired by the Lowell Observatory to go find this new planet. He had just was a farm boy from Kansas. He had made some of his own little telescopes and sent some pictures to Lowell Observatory, and they were impressed and decided to hire him to find these things. And he quickly realized that taking pictures like this can't show you what is a planet. You know, is it that? I don't know. Is it that? Is it that? Who knows? Clyde Tombaugh said, the way you do it, you take a picture one night, you come back the next night, you take another picture, and you see what moves. And sure enough, if you come back the next night and take another picture, it moves. You guys saw that, right? It was the one that moved. So it's actually a really impressive job that Clyde Tombaugh did. He spent more than a decade. He would take these big photographic plates. It's a big piece of glass with photographic emulsion painted on it, and he would take 2 or 3, and he would then have a machine where he could stick one here and he could stick another one here, and he would look through some sort of binoculars, and he could flip a little mirror back and forth and look sort of and blink back and forth between them. Exactly what we do now with the computer really easily, but he had to do this all by hand, and he looked at hundreds of these things that were about this big, and the section that we're looking at here is about this big. This is a tiny, tiny section of a tiny amount, and he looked through all of these things and only found one little moving thing. I'll show it again. Here's the first night. There's the second night. Anybody see it? Oh, sure you did. Okay, we'll try one more time. Here's the first night. See it? There's the second night. It's not that. People always point this thing out. It's not that. Anybody thought it was that? No. So I don't know why. I've talked to some friends who are in the field of physiology, and they explain to me that if you repeat something 3 times, the 4th time everybody always sees it. And I don't understand how this works, but apparently it works. There it is one night. There it is the next night. And that's it. It's a tiny, tiny little thing moving across there. It's not even a particularly bright star. And these are the actual discovery images that Clyde Tombaugh took back in 1930 that discovered Pluto, which when you look at these actual discovery images and realize what a small area this is and how much of the sky he looked at, you realize just what an amazing job it was that he found this. Regardless of whether we call Pluto a planet or whatever we call it, finding it back in 1930 was just simply an incredible piece of astronomical work. But even when Clyde Tombaugh found it back in 1930, he thought, this was not what he was looking for. He was looking for this thing that might have been this big, this planet X, this large object that we now know is not out there. In fact, Pluto is so small that we now know it's actually it's smaller than the moon. It's about half the size of the moon. And this is going to be part of the reason why we don't really consider it a planet these days. But it really is quite small. It's not nearly as big as any of the other planets. And the other very strange thing that was quickly learned about Pluto is that it has a very funny orbit. Here are the 4 giant planets. Jupiter, Saturn, Uranus, Neptune, all in nice circular orbits going around the sun, all in one disk going around the sun. You throw Pluto on there, and it suddenly ruins the entire nice, pretty pattern. Pluto has this crazy little orbit that dips inside the orbit of Neptune at this point. It goes further out here, and even more strange, if you looked at it on its side, Pluto is tilted by about 20 degrees with respect to all the other, I used to say, it's hard to say, all the planets. If you want to say all the other planets, it's not a planet. All the planets. So it never fit the pattern of the other planets, This is really quite hard. Never fit the pattern of the planets, because it's not a planet. At the time, though, there was a debate at the time. What do we call this thing? Well, there weren't that many options on what you call things in the outer solar system. What do you call it? You call it an asteroid. People knew about asteroids at this point, but the asteroids were all in this little band between Mars and Jupiter. They're all in here, not out here. No asteroids out there. A comet. Comets are known to have these orbits that come looping out and looping back in, and it kind of looks, like it might be a comet. But comets are defined by the fact that they have tails, coma. They have this gas expanding out from under them. So it clearly didn't fit the bill of comet. So by default, planet was really the only thing it could be. So sure enough, in 1930, it was declared to be a planet, and it had been a planet for the entire 76 years since, until about a month ago. to find, well, so Clyde Tombaugh found this thing, called it a planet, but still didn't quite feel things were right. And so he kept on looking. He wanted to find the real thing that he thought was the real planet X out there. And he ended up looking at a huge swath of sky. Here's a map of the whole sky. Picture this like a globe, only looking outward. So now this would be the North Star up here and the Big Dipper, and here would be the Southern Cross down here. Clyde Tombaugh looked at this whole region from all the way from down here to all the way up here. Huge, huge swath of sky. The line here that's labeled the ecliptic, that's the disk of the solar system. So that's all the planets are somewhere here on this line here. And so Clyde Tombaugh looked over the whole ecliptic, and he looked a good bit south and a good bit north, and found no other objects out there in the outer solar system except for Pluto. And in the end, I think he was a little disappointed that this planet X was finally not there, and Pluto really was the only thing out there. In the 65 years after this discovery, though, astronomers had started to re-look again at the outer solar system to see what else might be out there that was missed this first time around in the 1930s and 40s with the antiquated technology. And as of today, we now know that Pluto's not alone at all. Pluto, in fact, is a member of what we call the Kuiper Belt. And we know of now more than 1,000 objects in this region out beyond Neptune. Again, here are the giant planets: Jupiter, Saturn, Uranus, Neptune. Each one of these diamonds is an object out in the Kuiper Belt object, we call them, that some astronomer has found using essentially the same technique as Clyde Tombaugh. Take a picture, come back, usually not the next night, but rather a couple hours later, come back, take another picture, and look for the things that move. And sure enough, there are many of these things out there. When you have modern technology and larger telescopes, you suddenly realize that Pluto was just the tip of the iceberg. There are many, many thousands of objects out there, some of them approaching and even exceeding the size of Pluto. And Pluto is really just a typical member of this Kuiper Belt. There's Pluto, actually, the blue dot right there. And Pluto's orbit takes it from the inner edge of this Kuiper Belt out here to the outer edge of this Kuiper Belt. And it really encompasses the entire thing. So even back before the definition of planet was changed or not changed, whether you think Pluto should or should not be a planet, Pluto is without a question a member of this Kuiper Belt. And in the end, that's going to be the reason that it got changed to not a planet, because it's a member of this Kuiper Belt here. To find these 1,000 objects in the Kuiper Belt, astronomers have done something that looks a little strange. Now, Clyde Tombaugh, I told you, looked through this whole region of the sky looking for anything else beyond Pluto. Didn't find anything else beyond Pluto. Astronomers, in the first 10 years of looking at objects out here in the outer solar system, looked at this much sky. Now, I gave this talk to a third grade class, a similar version once. I showed this once, and a third grader raises his hand, and he says, well, okay, so how come astronomers are stupid now? And have to say that that's a really hard question to answer, because the reasons are vast. But the reason that astronomers have covered so little sky in the first 10 years, it's not because they're stupid, but it's because as technology improved, telescopes got bigger, detectors got bigger, everything got better, except for one thing. And that one thing got much, much, much worse. And that one thing was our ability to cover large swaths of sky at once. And the reason is simple. And it's something that most people don't think about when they think about the advances in astronomy. The reason is simply this, is that Clyde Tombaugh used, as I said before, photographic plates. A piece of glass, it's about this big, photographic emulsion painted on the back of it. And it was big. You could make a pretty big piece of glass, and you could paint a lot of photographic emulsion on the back of it. So you could cover big areas of sky at once. These days, all astronomers use digital cameras, CCD cameras, just like the digital camera that almost everybody has. And the very first astronomical CCD cameras 10, 15 years ago were tiny compared to the photographic plates. Here, the first size were comparatively about this size. Here's the full moon. Here's now what's considered a really big CCD at the big Keck Observatory. The screen is the size of Clyde Tombaugh's photographic plate. So imagine Clyde Tombaugh did a pretty good job of covering the whole sky with these huge photographic plates. If you wanted to do it with these, or even with these, I once calculated how long it would take with the Keck Observatory to cover the whole sky with this CCD, and it was something like 42 years if you took weekends off. And I applied for the telescope time for 42 years. They rejected me. I even had a couple grad students lined up, but it would be like 7 generations of grad students to do all the survey, but it didn't happen. So this was clearly not going to happen. So what's the solution? If you wanted to do like Clyde Tombaugh did and cover vast swaths of sky instead of just these little patches of sky, we needed to find some way of covering big areas of sky other than these little CCDs. The trick came about actually from something a lot of people have helped. In fact, how many people have bought a digital camera in the past year? So you guys are good people. How many people have bought it? How many people have never bought a digital camera? Okay, you're bad people. You guys have to. You have to leave right now. Every time somebody goes out and buys a digital camera, if you're like me, for example, and you buy a digital camera every year, not because I'm a camera aficionado, but because I lose mine every year. If you're like me and you buy a digital camera every year, what do you find? Well, your first year you buy one, and you spend the same amount of money every year, but every year the number of megapixels you get gets bigger, right? So the first camera I bought, I think it was, I don't know, it was like 400 by 800. Well, it was sort of small. The first kind of, when people were just starting to get those, and now, I don't know, for a couple $100, how many megapixels do you get? 10? I got to go lose my camera. I haven't lost it this year, and actually it's usually my wife's fault. She drops it in the water. Oh, that was me. She dropped it in the sand once, though. That was, but I haven't lost it this year, but I can't wait to go get a 10 megapixel camera. That's pretty exciting. So I ask this question every once in a while, too, and I'm always astounded by the new answer. What's the biggest number of megapixels that anybody has? Does anybody have more than 15?
Yeah, 20.
What? Does anybody beat 20?
No, the current big Nikon.
No, do you have one, though?
No, I
No, it doesn't count unless you have one. Who's got one? Anybody got a 20? 15? How many? 16 megapixels. Don't you guys wish you had a camera? What?
I helped make 16.
Doesn't count. I make things too, but doesn't mean I can afford to buy them. 16 megapixels is actually, this is fairly amazing, because when I first started this project, I would ask people this question, and it'd be 2. And people would say, wow, you have 2 megapixels. That's cool. And 16. And so in some ways, this next slide is less impressive than it used to be. So let me show you my next slide here. And we have our new camera that was built, because this camera is now 5 years old, down at Palomar Observatory, is this big, which is pretty good compared to what it used to be. It's 170 megapixels, which really, when everybody had 2 megapixels or 1 megapixel, 170 sounded really impressive. When you've got 16, it's 10 of your cameras. Okay, so it sounded good at the time, and it's getting less good. But it's a huge area of sky compared to what we had before. And we can reasonably expect to cover a lot of sky. This camera covers this much sky. If you hold your arm all the way out, make a circle, that's how much we get at once. So every time we open up the shutter, we stand out there and do this. And over the course of a night, we can do about this much. So most nights I go outside to check what we've done that night, and I sort of hold my hand up like that and say, yeah, okay, we've looked at that little section right there. It's not huge. It's not like you can do it all at once, but we've been doing this for about 5 years now, and we've done a pretty good job of covering big swaths of the sky. The other key component to this, of course, is having a telescope to put this camera on. The telescope that this camera goes on is the Samuel Ocean telescope, is one of the smaller telescopes down at Palomar Observatory. If you've been down to Palomar Observatory, a lot of you probably gone down there and seen the 200-inch telescope down there, which is an impressive telescope. And this kind of looks like the 200-inch telescope because they designed the dome to kind of look the same. But it's a very different telescope. It's a small, wide field of view telescope. And it's one that there are 2 really good extra properties. One, of course, it has this camera on it, so we can cover vast areas of sky. 2 is that it's a smaller telescope, so people are willing to give us large amounts of time on it. And the third, exceedingly important property of this one is this, which doesn't look like much. But boy, this is it. This is a microwave link. The microwave link goes to San Diego. From San Diego, the internet link goes to Pasadena. We run this telescope entirely robotically while we sleep. And what that means, it means several things. One, it means that my wife still talks to me. And it means that we can do this night in and night out without having to go down to the telescope, stay up all night. I have to teach classes. I have to, be home to pay my taxes, all that kind of stuff. So you can actually have a life and do this all at the same time. In the morning, the data get transferred from the telescope to my computer down at the Caltech campus, and I look at the data from the night before without actually ever having to lose too much sleep about it. You always have to lose some sleep, but it's not too bad these days. So what do we find? Well, what have we covered? This was what all the astronomers had done before we started. And since we started, and we've been doing this for a couple of years now, we've covered about this much sky. Yeah, here, try that again. We've covered about this much sky. That's a lot of sky. That's actually, I'm actually really thrilled to be able to show this because as I keep saying, we've been at this for 4 or 5 years now, and we finally have passed Clyde Tombaugh. For the first time since the 1930s, when he was doing this, we have finally done a survey of the sky that covers more sky than he did. And which just shows you what an amazing job he did with the technology from back then. We have a few spots missing. We can't see the southern hemisphere, of course. We've been looking to dig tunnels, but telescopes still can't point like this, so no southern hemisphere. This swath of sky that we generally avoid is the Milky Way galaxy. It's the galactic plane. It's if you look up in the sky, you see the Milky Way across here. And when you're looking for Kuiper Belt objects, if you have all those stars in the Milky Way in your background, it's almost impossible. So we generally don't look there. We still have a little bit to do up in the north here, and we have one patch. This one little patch right here, and right here is the northern winter sky. It's January and February, and anybody who remembers last January, or the January before, or the January before, or the January before. Wouldn't be surprised we don't have much data right there. We will, we hope, get it this January, and then we'll actually be done. We will have done all the sky that you can see from Palomar Observatory in the north, and we'll really be able to tell you all the objects that are out here in this range. So let me show you what some of these things that we find are and walk you through the process of how we do it. So we take these pictures of the sky, as I described before. We take a picture, we come back to the same spot, take another picture an hour and a half later. We come back one more time, take a picture an hour and a half later. And the data come down to the computer in Pasadena. The computer cranks through everything and looks for anything that moves. If it's not moving, it's a star, throws them out. If it thinks it sees something moving, it flags it and gives it to me to look at in the morning. And every morning, I probably look at 100 little postage stamps that the computer has picked out, of which every once in a while one is real. So we go through a lot of things that are not real, but it's actually very quick. It takes me about 15 minutes every day to go through all this. The ones that are real, let me show you a couple that are real. I don't know why it's doing that. Ignore this side, because it's not supposed to do that. So let's just look at this side. Here's a little postage stamp. In the sky, this postage stamp is about, I can't make my fingers that small, but it's about that small. If you can make about the size of a hair, it's about the size of a hair held at arm's length. Tiny, tiny little part of the sky. The computer has picked out something that it thinks is moving over the course of the 3 nights. You can see stars. The stars are all stationary. Star, star, star. Oops, and there's something that moves. Boom, 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 boom. Those are the 3 images, and it sees something moving very slowly over the course of those 3 hours. Now, there are a lot of things. If you take pictures of the night sky, you see a lot of things that move. And you can tell a lot about them just from how fast they move. The further away the thing is, the slower it moves. The closer it is, the faster it moves. So anybody want to guess what the fastest moving thing we see is? Airplanes. Palomar is in the path of the San Diego airport. So the problem with airplanes is that they're also really big. So they look like this. So they ruin the entire field. We have to try it over again. So we see airplanes every once in a while. We see satellites in orbit around the Earth. They move very quickly. Moving out further, we see many, many asteroids. Asteroids, again, if you remember, they're in this region between Mars and Jupiter. If you remember that picture I showed you of the solar system, from looking at that whole view of the solar system, that's a tiny, tiny area, and it's relatively very close by. So asteroids move very quickly. We're interested in the ones that move very slowly. We sometimes see these near-Earth asteroids that people talk about. And in fact, we're in close collaboration with the group right here at JPL who looks for the near-Earth asteroids, and we share data back and forth. So we don't look at the near-Earth asteroids, but we ship the data to them. So if they're ever, we take pictures of things that are about to smash into us and kill us, don't worry. We send the data to the right place. We'll get it all figured out. It might be a day or two too late, but we at least send it there. So this one is moving, compared to all the things that we see out there, I'll show you an asteroid here in a minute. This one is moving very slowly. But simply from its motion, we can tell you about where it is. This one's moving sort of a moderate speed. This is it's about the same distance as Pluto. And The other thing you can tell, you can try to guess at, and we'll talk about this more in a minute, is how big it is. And the way you tell how big it is from how bright it is, how much sunlight it's reflecting back at you. And so from this and the amount of sunlight, I know that that object is about the distance of Pluto, and it's not particularly big. It's about 400 kilometers across. So 400 kilometers across. Pluto, in comparison, Pluto is about 2,300 kilometers across. So it's a small fraction of the size of Pluto. But it's one of these new objects that we found out there. And I'm going to try to lull you to sleep by showing you a bunch of these before I bowl you over the head. Here's another one, a little bit brighter, moving about the same speed. So this one's about 600 kilometers across. This one's moving a little more slowly, as you'll notice, and it's a little brighter. So the fact that it's moving more slowly means that it's further away. The fact that it's brighter and further away means that it's even bigger. So this one's actually about a 1,000-kilometer object. And actually, oh, there's an asteroid here, too. See, look at the fast-moving one. One time it's up here. Let's see if I can do it. 1, 2, 3. There it is. 1, 2, 3. Oops, I can't do it. That's the asteroid. So there's an asteroid moving very fast that would have been picked out by the asteroid people here at JPL and sent in. So we see a lot of these things. We found something like 80 objects in the outer solar system in doing this, and they all look some flavor of this. Sometimes they move a little sideways instead of moving up and down, but they generally. Here's one a little bit slower, a little bit fainter. This one's out almost 50% further away than Neptune, and it's about 500 kilometers across. Blah, blah, blah. Here's some more. They just sort of all look the same after a while. That's all, they all look the same after a while, but every time you find one, you get a little charge. You're going through all the stuff, and you're sort of, nothing's there, nothing there, nothing there, and then suddenly there's this little thing blinking, and no one's ever seen it before except for you, and it's always a little moment of excitement. But every once in a while, you're sitting in your chair doing this, and the little moments of excitement almost make you fall out of your chair. And that's this one. All right, tell me what you see. It's slow, and it's really bright. It looks big, but all that means is there's a lot of light, so it's kind of saturated out there. So these things are all just little points, but it's really slow. This is actually about a factor of 2 slower than almost anything we'd seen before, which instantly tells you it's essentially a factor of 2 further away. Okay, that's enough to make you fall out of your seat to begin with, because we had found almost nothing at that distance in the solar system. But the fact that it was also, at the time, the second brightest object out there we had ever seen, and that far away, it was immediately obvious. Once I got past thinking, okay, we just did something really stupid. What did we just do really stupid? You could do things like if you took a picture of the same field 10 minutes apart instead of an hour and a half apart, it would look like it was moving really slowly. So I thought, did we screw up? And I looked at the times, and I looked at everywhere else, and I was like, no, this thing is really out there. Once you realize it really, really, really is real, then you immediately know this thing's bigger than Pluto. And so first thing I did was picked up the phone, and I called my wife. I said, I just found a planet. And she's like, oh, that's really nice. She was 3 months pregnant at the time. She said, that's really nice, and don't forget to bring the milk home tonight. And I forgot. But it was pretty exciting. This is some instant gratification. Well, instant after 5 years gratification. When you see it, you know you've seen it, and you get very excited about this. So there are a couple of things that you want to learn very quickly when you find one of these things. And one of them is what does its orbit look like? Is it going to fit that circular pattern of things that are planets, or is it going to fit that sort of crazy pattern? And the problem is, this one, it turns out, has a 560-year orbit. And to find out, to track its orbit, you have to look at it over some relatively significant chunk of its orbit. And so this is 3 hours. That's really not very significant, 3 hours. So that's not enough to figure out its orbit. So really the right way to do it is to wait a couple of years, track it, see where it's going on. And we just have no patience for that sort of thing. But the nice thing is, the thing is so bright, it was easy to find in everybody else's old data. So many people have seen this thing before, but what they were doing some other type of project. They weren't taking a picture and coming back an hour and a half later looking for something that moved. They were just taking a picture for other purposes. So we could find it. We found it all the way back to 1950 was the earliest images that we found it in. We're pretty sure that we could find it in Clyde Tombaugh's original photographic plates, but Lowell Observatory appears to be a little reluctant to let us look. I can sort of understand why. I mean, I don't think they want it to be like, oh, Clyde Tombaugh screwed up by missing it. But it's not that he screwed up by missing it. It would have been very faint on his plates. If you knew where you were looking, I think you could see it. There's no reason he should have seen it. So I'd kind of like to look just for just for fun, but they don't answer my emails. Anyway, so we got it back to 1950. So what does the orbit look like? That's the question. What does the orbit look like? The answer is it's even crazier. So here's again Jupiter, Saturn, Uranus, Neptune, Pluto with that crazy elongated orbit. Well, look at this. This thing is even more crazy elongated. And what's more, the reason it's so far away, the reason it's moving so slowly, is because it's right now at the furthest point that it ever is on its orbit, which also means that that's the most distant it ever is, and the most, yeah, of course it means that. It means it's the faintest that it ever is in its orbit, which is bad news. We're unlucky in some sense. This thing is pretty bright, but if it had been here, instead, it would have been much brighter, much more easy to study. But the bad news, or at least the good news, is that if it had been here, Clyde Tombaugh would have certainly found it. And he would have found not just Pluto, but Pluto in this next one. And then that would have caused all sorts of mess. So it's probably better that Clyde Tombaugh didn't find this one. There was only one that he found that made it. Actually, in some sense, if he had found two of them out there that sort of had these weird orbits, people, I think, would have had an inkling that there was something like a Kuiper belt out there. And it would have been interesting. But it would have kept us from having all the fun. So we're happier it's out here. Remember that Pluto is tilted by 19 degrees compared to the disk of the other planets, which is bizarre, right? So this thing is 45 degrees. 45 degrees. Nobody currently has a very good explanation for why that is. We find other objects in the Kuiper belt that are tilted by a few degrees, 10, even 20, 30 degrees. 45 degrees is really more than anything else. And to find probably the biggest object out there in the Kuiper belt to be tilted by that, like that is really quite a surprise. Presumably, Neptune is to blame in some way. But we don't quite know if there's anybody else that's part of the picture or exactly how it got there. So this is still an interesting mystery that we're currently trying to solve right now. So that's the first question that we always want to know. The first question that everybody else always wants to know is, how big is it? So this is where I have to describe to you the problem with why we don't actually know how big these things are right away. And the reason is because you saw that picture. You saw that picture of that very bright object moving across the screen. And so it looks bright. Why can't we figure out how big it is? Well, what you're seeing there is just like when you look at all the planets, you're seeing sunlight reflected from the surface of that object. It takes 12 hours to get out there. It takes another 12 hours to get back. So you see yesterday's sunlight, but it's sunlight reflected from the surface. And you see a lot of sunlight reflected from the surface. Okay, so why can you get a lot of sunlight reflected? Well, you can get it for one of two ways. You can either have a relatively small object, but with a very shiny surface, snow-covered surface or something, and that'll reflect a lot of sunlight. Or you could have a really big object with a much darker surface, but it still is big enough that it reflects all that sunlight. Either way, you get the same amount of sunlight reflected back, and you can't tell which one that is just by looking at it right there. So astronomers have come up with these very clever ways of using imaging from things like the Spitzer Space Telescope that's up in space right now to figure out how much heat is coming from the object and sort of indirectly figure out how big it is. And there are all these very complicated ways that are difficult to calibrate. And we're less clever than most astronomers, so we decided to try this sort of dumb way. And so we tried this where it's clever, maybe. We decided to take pictures with the Hubble Space Telescope and see how big it was. We thought that was, maybe that would work too. So, okay, why do we do? Usually you can't do that. Most of these things are so small that even with the Hubble Space Telescope, they just look like a point of light. But because we knew this thing was bigger than Pluto, even if it reflects a lot of sunlight, it has to be bigger than Pluto. Since we knew it was bigger than Pluto, we knew we would be able to see the disk of it with the Hubble Space Telescope and then measure precisely how big this thing is. So I'm about to show you what is probably the best picture of this largest dwarf planet in the known universe that most of you will ever see in your lives. Maybe I can imagine that maybe sometime there'll be a telescope up there that can do better. But right now, this is as good as it gets and probably the best you'll ever see. And that's not it. There it is. Yeah, okay, so not very exciting. That is the best picture you'll ever see, though. It's kind of sad. But so it doesn't look like much, but it is actually a fabulous, fabulous picture because the Space Telescope is such a good, stable, high-quality instrument. Even the Space Telescope, which is supposed to be perfect, changes around a little bit, has some problems is not the right word. Just when you take a picture with the Hubble Space Telescope, for most people's purposes, every picture you take will look exactly the same. But when you're really working on the very edge of what you can do, you have to be very careful. And so to make sure that we knew exactly what the telescope was doing, there's actually a bright star that's right here that I'm not showing you. And we did this 32 times where we took a picture of the star and this thing at the same time, star, object, star, very precisely calibrated what the Hubble Space Telescope was doing to figure out exactly how big across this thing is. And believe it or not, this is the part where no one believes what I say, but believe it or not, it's exactly as big as the red dot there. And all the rest of that stuff that you see are the effects of the telescope itself. But we very precisely calibrated it. The size is 2,400 kilometers with an uncertainty of about 100 kilometers. Again, I'll remind you that Pluto was about 2370, depending on who you ask. So this thing turns out to be just barely bigger than Pluto. It's about 5% bigger than Pluto. The interesting thing is, when we first discovered it, our best guess would have been that it was 25%, 30, maybe even 40% bigger than Pluto. This thing is much smaller than we had initially guessed. The reason is, if you remember back to my whole explanation of reflected sunlight, you could be big if you were dark, and you would be small if you were really reflective. This thing is one of the most reflective things in the solar system. It reflects 87% of the sunlight that hits it. The Earth reflects, somebody help me out here, it's 42%, is that the right number? Somebody must know this. Come on, we're JPL. I think it's 42. I always forget what exactly number is. 34, 42, 21, I don't remember the number. Some, small amount. Fresh fallen snow is 80-ish percent, 70, 80%. 87% is a lot of reflection. I mean, this is an incredibly bright, reflective surface. Why? Why would this thing be one of the most reflective things in the solar system? I think we know the answer. The answer is that this object that has, just like Pluto does, when it's close to the sun, or relatively close, when it's close to the sun, it has an atmosphere like Pluto's. Pluto it's a thin atmosphere, but it's an atmosphere. It's mostly nitrogen, which is sort of funny. It also has methane in it and some other things in it, but it's mostly a nitrogen atmosphere, just like the Earth's. When you move it further away from the sun, that nitrogen atmosphere freezes onto the surface. If you took the Earth and you moved it to where the dwarf planet is there, the Earth's atmosphere would freeze, and you would get about a 30-foot section of nitrogen ice on top of the Earth. And it would be really reflective if you saw it out there. And I think that's what's going on. It's actually, to my mind, this is actually one of the more interesting sort of atmospheres in the solar system. It's the only object that we know that's big enough to have an atmosphere, to maintain an atmosphere on it, but also has an orbit that's elongated enough that that atmosphere comes and goes with its 580-year season. So it's going to be really fascinating to see that atmosphere reappear as it gets closer, and I'm really looking forward to making those observations in another 280 years. Well, okay, so we don't get to do everything. We have to leave something for the kids, but it is a really very interesting object, fascinating atmosphere out there. So. But of course, it's 2,400 kilometers. It's not that much bigger than Pluto, and the problem, of course, with Pluto was that it was not really that big at all. This thing, though it's the largest object that we currently know of in this region of the Kuiper Belt, it's not very big compared to the rest of the planets. And so this is the part where I have to go into the editorial comments about what's a planet. And I still haven't quite figured out how I do this editorial at this point, now that there's actually a definition of what's a planet. But I'm going to start from what I would have told you a month ago or so, 2 months ago. And it'll explain to you, I think, in pretty reasonable ways why Pluto's not a planet, why some people think it is, all these things. So if you were an alien, some of you might be. We are at JPL. You have to be worried about those things. But if you were an alien and you were coming into the solar system for the first time in your spaceship, and let's say, in fact, you were born on the spaceship, so you've never seen a planet before, and your alien life form has no word for planet, what do you see? Well, first you see the sun. You're going to the star, and you're driving along towards the star, and then you see this big extra bright thing next to the star, which is Jupiter. Then you suddenly notice Saturn, Uranus, Neptune. So you realize, wow, this is not just a star. There are 4 things going around the star, and you get very excited about these things because aliens get excited about stuff like that. You keep on going along, and you're like, oh my God, there's more. There's more. You suddenly see Mercury, Venus, Earth, Mars. There are 4 more things going around there, and you might take the 4 bright ones and you'll put them in this category, and the 4 next ones and you'll put them over here, and then you keep on driving in, and you get a little closer, and you realize, hey, look, between Mars and Jupiter, there's a swarm of material. A bunch of objects, the things that we call asteroids. You're like, wow, that's fantastic. We'll put these over here. And then finally, as you're getting even closer, you realize outside of Neptune, there's another swarm of objects, the Kuiper Belt objects, and you put this swarm over here. This is a very rational way to categorize the objects in the solar system. There are 8 large, important objects in the solar system, and then there are 2 populations of objects in the solar system. There are other things that don't quite fit the whole pattern, but this is one very simple way and very obvious way of classifying the solar system. And in your alien mind, you might be forgiven as an alien if you wanted to call the 4 big ones planets, and you might want to call these 4 other ones something else. So Jupiter, Saturn, Uranus, Neptune are the only planets. I've actually tried to teach this in my classes at Caltech, but they don't buy it there. Everybody kind of wants to keep Earth as a planet. I don't know. Sentimentalists. So we'll give you 8 planets. We'll group all these together, these 8 planets, and then these other things here. And that's essentially the definition that the International Astronomical Union accepted a month ago. And you'll hear there still are arguments back and forth about whether this is a sensible definition or not. And it's hard to... astronomers are not above trying to be politicians at the same time. So it's hard to separate out the politics of this from the science of it. So I'm going to try to help some. Because some astronomers will say, well, this definition is crazy. It makes no sense. That's politics, and that's smokescreen. The definition in astronomy and in most sciences, we don't tend to focus on a precise definition of thing. We focus on the concepts. The concept of these 8 dominant objects is a very, very clear concept, and it's a very clear classification system. The wording of the definition is not terribly important. The vote was that this is the right way to classify things as planets. Some people are actually arguing a much more interesting case, which is that there is an alternative way to classify things in the solar system, and that's to say, take an object and put it in a box and ask it what it is. And if it's big enough to be round and have important geological things happening on a surface, let's call it a planet. And that's also a perfectly sensible way to categorize things in the solar system. It would give you, instead of having 8, you would actually add a lot of these things over here into this category, and you would end up with a couple of hundred things that you'd call planets in the solar system. Which definition is right? It's a stupid question. The word planet, it's a weird way to do it. The word planet has existed for a long time. These scientific concepts are relatively new. And so both groups, although I like the 8-planet group, I think for my taste, make the most sense. But both groups are essentially trying to sort of hijack this word that already exists to mean their scientific definition, which it never was meant to be. So I think the whole thing is a little bit crazy. And I had proposed what I thought, of course I thought, it made absolutely the most sense. It was the only sensible thing to do because I proposed it, which is that the word, given that the word planet, I think you can see, given that there are many different alternative ways to classify things, no one of which obviously means planet, it's pretty clear that the word planet is not a scientific word and need not be given a strict scientific definition. So I would have preferred to sort of take the analogy from the word continent that geologists have. If you haven't figured it out by now, the word continent actually has no scientific definition. There is no reason that Europe is a continent. I'm sorry, probably there are people from Europe here. It's not a continent. It makes no sense, right? Australia, just a big island. But of course it is. Why is it a continent? Because culturally we've always called Europe a continent. Well, I think they came up with the word, so they kind of grandfathered themselves in. India is a subcontinent. Does anybody know what a subcontinent really is? India. I think that's the answer. The subcontinent is India. There are no other subcontinents, are there? Indonesia is sometimes kind of, it's called a, I've heard some words for the whole like Indonesia and, I don't know. Anyway, it's like a micro, yeah. You know, geologists don't care. Geologists will not sit around and argue, yes, Europe should be a continent. No, it shouldn't. We're going to define it to be not a continent. Yes, we are. And have these fights about it. Australia must go. Geologists, you can talk about continents all day long, and geologists will not argue with you. They'll talk about the science. They'll talk about continental crust, continental collisions, continental plates, continental dynamics, but they will not debate with you the word continent. If they did, I would insist that I think Madagascar really deserves to be a continent. It's the smallest thing that's actually on its own plate in its continental crust. You would say, who cares, right? Who cares? And I'm going to tell you who cares. Is there anybody in this room who's been to all 7 continents? Nobody? Oh, come on. All right, who's been to 6? 6, what have you missed? Antarctica. What if I told you that Madagascar was a continent? Ha ha, you've only been to 6 of the 8. You missed them all. Or what if you had spent $50,000 to go to Antarctica and then I told you, oh, but it wasn't a continent anyway? You would kind of care, right? A little bit, just a little bit. Who cares? Culturally, we care about these things. Continents are kind of the way that we wrap our minds around the geography around us. And planets are kind of the way that we wrap our minds around the solar system. For most people, if you ask them to start describing their neighborhood, first, they can describe their house, their neighborhood, their city, their state, their country, their continent, the world, the solar system. That's pretty much it, right? Most people then at that point say, and then it's either stars or galaxies or I'm not entirely sure what's out there. And that's okay. But so planets are part of your neighborhood. And this is why, I understand the people who are very upset about Pluto being demoted, because it's telling you that Australia is not a continent. It's exactly the same thing. Luckily, there are no people from Pluto that are big and drink a lot of beer that would beat you up if you said that. But anyway, so for my taste, I would have been perfectly happy if we had said, hey, we're going to come up with new words. Something needs to describe these 8 things and these 8 things, and we'll come up with a word for that. Something needs to describe all the things that are round. I think the word sphere works pretty well for that. But the word planet, it's cultural. We're not touching it. You can have 9, you can have 10. 10 would have been good. But that view, the IAU, the International Astronomical Union, really felt the pressure to come up with a scientific definition. As scientific definitions go, I think the 8-1 works better, but it's essentially an aesthetic choice. It's a religious choice. If you like 8 because you like the sort of this classification, you'll agree with it. If you don't like this, you won't agree with it. There is no science there. It has nothing to do with science at this point. It's religion or aesthetics or something. I can tell you why I like 8 better. It sort of historically makes more sense. The same thing happened to Ceres, the asteroid, back in the early 1800s. It was originally thought to be a planet. And when people realized that it was just part of a population, they said, nope, not a planet. We're going to call you a minor planet or an asteroid. And so the 8-planet definition is a closer match to the historical definition, which I like. And then it's just aesthetic. I actually like the word planet to be special. 200 planets, I don't like. And that's actually the most honest explanation I can give you. I don't like 200 planets. And it's purely aesthetic. So if you like 200 planets, more power to you. I have to warn you, though, most religious arguments like this get settled by slaughter. So I have a stick, so don't start with me. So anyway, that's the long explanation why Pluto. If you took a random sample, ignore the statements from the people who are unhappy about it that, oh, this was a small group of astronomers, blah, blah, blah. If you take a general sampling of astronomers, most of them will support the 8-planet view for purely aesthetic reasons, and it's not a scientific argument. Some will take the 200-planet view, also for aesthetic or perhaps political reasons. That's fine, too. The debate should not continue because it's not interesting at this point, arguing back and forth about this, but it will. That's back to that thing about astronomers being stupid. I can't answer this one. It's a long story. So anyway, so it's not a planet. It's a dwarf planet. Oh, so dwarf planet now, for those of you who are wondering what the dwarf planet part means, a dwarf planet is something that looks like a planet, but's not a planet. It's the easy way to say it. Looks like a planet means that it's round. It's that same category that we were talking about, things that are round. Put it in a box, ask it the question, hey, are you a dwarf planet? It says, well, I'm coming around. That's a dwarf planet. So there are many of these. So now there are sort of 200 dwarf planets. We currently know of, I think, about 35 things that fit the bill for dwarf planet. We'll find hundreds. There will be many dwarf planets. That doesn't bother me. As many dwarfs as possible. And of the ones, UB313 is the largest of the dwarf planets. UB313 now has a real name, and the name is Eris. Eris is the Greek goddess of discord and strife. We just picked, it didn't mean anything. We just picked it. She's the one who caused the Trojan War by causing quarrels amongst the goddesses. Her favorite method of causing discord and strife is to cause quarrels, is to cause people to think that they're right and everybody else is wrong, and to fight about it. I think it actually fits very nicely. And somebody said, well, isn't this, everybody will kind of forget about this fight in a couple of years, and then you're stuck with this name. I remind them that Pluto's the god of the dead. It's these. What was up with Clyde Tombaugh? I mean, this is Eris is a good Greek mythological name, and I think that this sort of showdown over Pluto, even though I hope it's now to rest, I think it's an important part of the history of astronomy, and I think it's a fantastic opportunity to teach people about the solar system and these populations in the solar system. So I have a hard time remembering Eris. I keep on wanting to call all sorts of other names, but Eris is the new name, and of course Eris is joined in its new name by its. Here's my old one. Here's my arguments. My arguments were very sophisticated, so I want to boil them down for a second for you. Let's see. Pluto should be called a planet because it has been on the list of planets for years. True statement. Your planet is bigger. If Pluto's a planet, so is yours. Impeccable logic, except Pluto is not a planet. So it was worth a shot. Anyway, Eris. Eris has a satellite. Having a satellite is great. And a lot of people say, oh, well, this means it's a moon, right? No, it doesn't mean it's a moon. Mercury and Venus don't have satellites, for one. And also, it turns out that of these 1,000 Kuiper Belt objects that I showed you out there, something like 10% or more have satellites, too. So having satellites is not uncommon. Scientifically, though, it's fantastic. Scientifically, what that allows you to do is to figure out how much the object weighs. And the way you do it is that you get to watch the satellite going around the object. If it goes around fast, it's because this thing is really heavy and pulling it around quickly. If it's much more sluggish, then it's a light object. We know how much it weighs. We know how big it is. That means we can figure out how dense it is, what it's made out of. Is it made out of uranium and this tiny heavy thing, or is it just a little snowball or something in between? The answer is probably going to be it's some sort of combination of ices and rocks. But by figuring out the orbit of this little satellite going around here, we'll be able to figure out exactly, or at least get some idea of what this thing is made out of. So we're very excited about this. The discovery of the moon. The moon's name is Dysnomia. It's a funny name. You can shorten it to Di if you prefer that. We tend to just call it Eris and Di are the two. Dysnomia is the demon spirit of lawlessness, and the daughter of Eris. And anybody who thinks a little bit might figure out why we chose that name. And people who think even harder can figure out that there are several reasons why we chose that name. But those are the mysteries for the day. We discovered Di a year ago, and we finally got back to the telescope just 2 weeks ago now, and now have the complete orbit around. So we actually are just about ready to calculate how long this orbit takes around and how massive it is. And within the next couple of weeks, we hope to have the answers to that. So we're actually pretty excited about that. As science goes, having this moon is an incredible boon, and we're very excited about it. And plus, we really like the name a lot, even though it sounds a little funny. So the other cool, old names. There are some interesting things about the moon, even before you figure out what it is. And one interesting thing is that if you take the Earth and the moon and you shrink them down by a factor of 5, shrink down the Earth itself and shrink down the distance between the Earth and the moon, you actually come up very close with the same general-looking system of, let's see, Eris and Dysnomia. Are these two? And they look about the same. It's about the same scale, the same general scale, just a little bit smaller. And that all sounds, it's an interesting coincidence. But actually, we're fairly convinced that there's actually real science behind that, and that Eris and dysnomia were formed in the same sort of way that the Earth and the Moon were formed. Most people these days believe that the Moon was formed when a sort of Mars-sized body smashed into the Earth and spewed off some debris, which went into orbit around the Earth, and that debris eventually coalesced to form the Moon. We think that the same exact process went on here, just at a much smaller scale. And by tracking down the orbit of this, we'll be able to answer these questions more. So again, I'm sneaking in some actual science in here. We're pretty excited about the actual, finding these things is all well and good, but it's actually the science behind it that keeps us going that we're most excited about. Whoops, I can't have that anymore. So, no idea who that was. I want to end with two different things. And the first thing, I've talked all about Eris and dysnomia, and I've really neglected some of the other objects that are out there. And there's some of them that are just really cool that we don't want to pass by. And as I said, we found something like 80 objects, but there are two that I think are worthy of interesting study in their own right. And one of them is this one. We show it as an elongated, rapidly rotating sort of football-shaped thing because, in fact, it's an elongated, rapidly rotating football-shaped thing out there in the outer solar system. This is supposed to be Pluto, the size of Pluto. Here's Eris, a little bit bigger. These things are actually to scale. This thing, back in the days when I was kind of thinking that if you were bigger than Pluto, you were a planet, I kind of had hopes for this one because this one's bigger than Pluto now, and now, and now. As long as you kind of go like this, you have to tilt sideways. This thing is crazy. It spins every 4 hours. It's the fastest rotating thing out there in the outer solar system we've ever found. It's elongated by a factor of about 2 to 1, and it's because of that spin that it's elongated. It has 2 moons going around it, and we think that it too was the product of one of these big impacts. Some large object smashed into it, made it spin, ripped off all of these ices that were on the sun. Some of them went into be moons. We actually have found what we think are chunks of this big impact as other Kuiper Belt objects now. We found 4 things that we are pretty convinced are chunks of this thing. So this one is really a fascinating object that we're studying in gory detail. Just like this one was called Xena for a long time because we give these things nicknames. This one we found at Christmas, so that we call this one Santa. But it's going to get a real name soon, and there will be an interesting story behind that, I'm sure. The other interesting object is this one, which is just a little bit smaller than Pluto, but actually, if you look at it, it looks very much like Pluto too. So where it used to be Pluto was the only one of these large objects out there, and in some ways it was kind of the oddball at the edge of the solar system. And I was always excited about this New Horizons mission that's going to Pluto to study it, and because I wanted to see what Pluto was like. But now I'm even more excited. Now, instead of just seeing this little oddball at the edge of the solar system, we're going to see a representative member of this class of very big objects out there and learn an awful lot about all of these by just studying this one that happens to be very close and easy to get to. And I want to end, the very end, with one last thought, which is to remind you that Clyde Tombaugh looked at this whole region here. We've looked at a region even bigger than Clyde Tombaugh, so we're almost done with a survey. But we have our sights even further away right now, and our sights have been set by this one object we found 2 years ago, 3 years ago now, 2 years ago now. What is this? Is this 1996? 2 years ago. And this is the object that some of you may have heard about. The official name is now Sedna. And Sedna, here's the Kuiper Belt again, or at least as it was 2 years ago. And Sedna is way, way out here. Now, it's a little bit unfair because actually Eris is right here. But at the time that I made the slide, we didn't know about Eris. But Sedna was right here. And just like when we found Eris, we really wanted to know its orbit. Is it in a circular orbit like a planet? We didn't know how big it was. It was bright. We thought there was a good chance it was bigger than Pluto. We were hoping it was going to be a planet. And in our minds, if it was a planet, we kind of wanted it to have a circular orbit. So we thought, okay, is it going to have a circular orbit like this? Or is it going to be more like a cometary orbit, like the one that Eris turns out to have, where it comes in close and goes out? And we were really, really curious to know. And the answer was, well, it doesn't actually fit. You have to do it here. And the answer is it does this. This is totally crazy, unexpected. It has a 12,000-year orbit around the sun. And we just happened to catch it at its closest point right here. Nobody expected anything like this in the outer solar system. And for reasons that I don't have time to go into, this is actually, in my mind, probably the single most exciting scientific find in this whole survey we've done. We're going to, by studying this object and finding more like it, I think we're going to learn just an incredible amount about the birth of the sun and what kind of environment it was in. But the interesting thing about it is we found it right here. If it had been a little further away, we wouldn't have been able to see it. It would have been too faint. There was a small period, about a 200-year period here, when we could see it out of 12,000 years. Okay, so either that means, so that's 1 in 60. Either that means that we're pretty lucky and we hit that 1 in 60 lottery and we should be going buying more lottery tickets. Or astronomers don't tend to like to think that they're lucky. They tend to think that, okay, if there's a 1 in 60 chance of finding it and we found it, probably it means there are 60 of them. Maybe it's 30, maybe it's 90, but it's a pretty good chance that we didn't just get lucky and find the one that happens to be here. So there are probably 60 objects the size of Sedna. Sedna is not small. Sedna is about 3/4 the size of Pluto. If there are 60 that are 3/4 the size of Pluto, you don't really know what the biggest one is, but you could make some educated guesses. And your educated guess would tell you that the largest object in this region out here that you could find is going to be probably the size of Mars. Maybe it's the size of Mercury. Maybe it's the size of the Earth. But there are going to be very large objects in this region. This is the whole solar system now. Here's the Earth in here. This is the last planet, Neptune. We're talking about this region here where there are going to be things bigger than some of the things that we call planets in here. Scientifically, this is going to be an incredible boon. Culturally, I can't wait because, of course, it'll be fun. It's going to be fun to find the first dwarf planet that's bigger than a real planet. So we don't do this just to make it difficult for the International Astronomical Union, but that's just a side bonus of doing these things. So we're out looking, and we just started this new search for these very distant objects in the last 2 months. We hope within the next couple of years we really have found some of these really big ones. And so the next time when I'm telling you about the largest dwarf planet in the known universe and showing you the view, it won't be this view from the very now close by Eris, but it'll be the view from much further out at the largest dwarf planet that's bigger than Mars in the known universe all the way out here. So thank you very much, and I hope to tell you more soon. Can we leave that open? They don't listen to me. So, questions? I try very hard to start in the back because I always ignore the people in the back at first. So there's one in the back. There we go.
Do the orbits of these new planets intersect any other orbits of that are?
Sorry, there are no new planets.
Of these dwarf planets intersect orbits of our planets, like Neptune.
Yeah, absolutely. Pluto barely crosses in the orbit of Neptune, as you saw. Some of the other, I said there was something like 200 dwarf planets. A few of them will also cross in Neptune's orbit just by a little bit, just like Pluto does, for very special reasons. It's been a little confusing because some people say, oh, but that means that Neptune's not a planet because it hasn't cleared these out. Neptune actually has done better than clear them out. It's actually forced all these things into these orbits where they cross just barely, and then it pushes them further away. So there are I haven't actually looked at the list to see how many of them are going to be the Neptune crossers, but there will probably be a few that also cross Neptune like Pluto does. Next question.
Why did it change names? Why did it go from Xena to Eris?
Well, why did it change names? Why did it go from Xena to Eris? So Xena was never supposed to be the real name. The real name, so the naming is done by the International Astronomical Union, and they can be very fast about these things, and they had a process set up 13 months ago when we announced this that was supposed to be almost instantaneous. And then it got waylaid by the fact that nobody knew what to call this thing. Is it a planet? Is it not a planet? What are we going to call it? Blah, blah, blah. So we were being good people and letting them do it their official way. But we always give these things nicknames for ourselves when we discover them to talk about. So there are 3 of us who are involved in doing this research. Mostly, I should mention the other 2. It's Chad Trujillo, who's out in Hawaii, and David Rabinowitz at Yale University. And the 3 of us find these things. We study them in detail. We have numbers for them. This one was K1021c, which is not nearly as memorable as Xena. So we use Xena just to remember what it was. When this thing didn't get a name from the IAU for a couple of years, I think that the name Xena first slipped out in an article in the New York Times when they asked me, well, what do you guys call it? I said, well, we call it Xena because we have to call it something. And then that got repeated about 100,000 times until it kind of got to be the name that everybody knew. But it was never going to be the real name. It's there was some argument that that modern mythology is equally valid as ancient mythology as a naming convention. And we toyed with the idea of trying to see if Xena would stick, but in the end, it's a tad embarrassing. And the next person would come along and name a planet Spock, and that would be all over with. So I'm a little sad to see Xena go, but her spirit lives on. Yeah.
On that image of Xena, if you will, taken by the Hubble.
Yeah, Eris.
Eris.
It's hard for me too. Eris.
No, it's okay. There was some irregularity there. Is it thought you can deduce any of the features of the
No. All the irregularities were due to actually irregularities in the mirror of Hubble, even just tiniest things. And so if it had been a little bigger, since we didn't know how big it was going to be at the time when we took the pictures, we really were hoping that it was maybe twice the size. If it was twice the size even, we could have eked out some features. But I think there are no features to be seen. And because if it's reflecting 86% of the sunlight, it's white. Yeah. So, and we actually, a lot of astronomers have spent a lot of time trying to see if they can see it rotate, see any kind of variation as it rotates. So far, to my knowledge, nobody has seen anything. So I believe it to be pretty featureless.
How do you spell Eros?
Eris, E-R-I-S.
E-R-I-S.
Yeah, not Eros, which is another god, or Eris, which is actually Eris's brother sometimes, or Mars. Yeah. So E-R-I-S, very simple, and D-I. We like that one too. Yeah. Oh.
I noticed in your map of the, I'm going to say Kuiper Belt objects, it looked like there was one region over there.
Oh, yeah.
Is that winter sky, or is
No, I'll show this again real quick. I should have mentioned that. It was obvious when I showed the other version of it, but when you look at the overview plot of all the Kuiper Belt objects, you say, hey, look, there aren't any down here. And it's just that region of the Milky Way galaxy where people don't look. So there are plenty of them down here if you could get all those stars to get out of the way and see them there. So there might even be big ones there. There could be something bigger than Eris hanging out in there that it'll take another, probably 50 years before those things have moved out of the galaxy and people start to look again. So it's not too late. Somebody else can find something even bigger if they keep looking. Yeah.
What's the Oort cloud?
The Oort cloud. So a lot of people have heard of the Oort cloud. There's the Kuiper Belt, and I was showing these things that are really far away. The Oort cloud, if you took this slide of the Kuiper Belt, and if you remember my slide that showed Sedna, where Sedna was here and its orbit went all the way to the next building over here, the Oort cloud would be about an Arcadia. And it's the Oort cloud is the very, very edge of the solar system. It's this essentially spherical group of very very vaguely bound bodies that are, it's not really the right word, but they're just on the edge of being ripped out of the solar system by passing stars, but they're just barely held to the sun, and every once in a while they get a little bit of a kick and they come in and become comets and they come screaming back out. So it's so far away. It's about 10 to 100 times further away than the furthest that Sedna ever gets. So they're really, really far away. I doubt that we will ever really directly see something out there in the Oort cloud in my lifetime, although astronomers tend to be clever people sometimes, so someone may come up with a clever way of doing it, but it's going to be really tough. They're really far out there. Okay, let me go down to the front.
Yeah, is there any chance that there actually may be a planet, an area that's clear?
Oh, yeah, this is my favorite question. Are there any other planets? Right? There are 8 planets. This is one of the questions everybody asked. What would it take to be a planet now? There's been some email debates going on amongst astronomers these days of really what you would have to be. You would have to be something like, if you were out at, say, 10 times the distance of the Kuiper Belt, and you wanted to really clear, then you would actually have to get picky about what the definition really meant. So then what does clear your area really mean? Well, you would probably need to be bigger than the Earth, maybe not quite as big as, say, Neptune or Uranus, but you'd have to be pretty big. Hard to imagine how something like that could get out there and be in a nice sort of circular orbit like that to have a small area to clear. Doesn't mean it's not there. I mean, I actually, in some ways, you would think I would hate this definition, right? My poor 10th planet got taken away. I can't go find any more planets. In some ways, I kind of love it. It now is quite a challenge to see what else there might be out there that you could even think about considering to be a planet. I think something the size of Mars would challenge our ideas of what planets are again. But something that was really big enough to clear its zone probably can't exist, but doesn't mean we're not looking, I think is the answer. Yeah?
When you find a new object, how are you concluding that its orbit geometry is so vast and so far out? You mentioned 12,000 years. And
Yeah. It's a good question. So as I told you before, for Eris, we went back all the way 50 years. So we could find it in all these pictures 50 years ago. It's a long and sort of fun process. You take pictures of it. You take pictures for maybe a month, and then once you have a month worth of pictures, you can predict where it should have been last year. So you go back to last year and you see if you can find anybody's pictures from last year. And sure enough, you think you find it, but you're not sure. You say, okay, if that's really it, then I should be able to predict where I was 2 years ago. And you go back 2 years ago, yeah, there it is. And so you sort of leapfrog back for as many years as you can. Sedna, we only went back about 10 years. So when I said 12,000 years, it might be 10,000 years, it might be 14,000 years. There's some uncertainty there. But still, 10 years is a short period for there. But if even from your high school physics, if you can bring your mind all the way back to that, all we need to know the entire orbit for all time is where it is, its position, and its velocity. And if you know any object's position and velocity and what else is affecting it, which is just the sun, you know everything. So we don't have to follow it for 12,000 years. We just have to make a good measure of its position and velocity. And with 10 years of data, we can do that pretty well. All the way back.
How do you guys factor the temperature difference or the size and density when you calculate the size of the planet?
Yeah, it's one of those things that we're going to have to do. So when we calculate the density, we'll calculate the density simply by how much it weighs and how big it is. So that's the density. Then the question is, what is it made out of? Well, ice has a different density depending on exactly the temperature, also depending on how compressed it is. So if you took a ball of ice and turned it into a dwarf planet, not a planet, this big, it would actually get more dense too. So it's a little more complicated than just saying, yep, here's the density, go down the periodic table, it must be made out of bismuth. So yeah, there are some more complications to do. Yeah.
Was there anything to say that the people were upset about Ceres being divided from a planet?
They apparently are happy because in the end, Ceres used to be just a plain old vanilla asteroid. It was going to be a planet for about a week, but now at least it's a dwarf planet. So there's a mission going to Ceres.
150 years
Oh, back then. Oh.
This is my third graders were asking.
I don't know the answer to that. I don't think so because it's just Ceres didn't have the Disney character going with it. So that had happened. But I don't actually don't know the answer to that. I don't actually know. Yeah.
I read your comments following the conference, and I really want to commend you for taking the high road. And Mr. Stern wasn't so gracious, but I still can't get it clear. What was it about the new definition of the planet that excluded Pluto?
It really, so again, forget the wording of the definition, because astronomers and scientists in general don't deal precisely with definitions that are, this is the definition, therefore it's this. They deal in concepts. So the concept of the definition is very simply that one that I laid out up here. Pluto is part, and only a small part, of this huge array of objects in the vicinity around it. It's like picking up a handful of gravel and saying, okay, the biggest one, we're going to call this a planet. It's a handful of gravel, and then there are 8 boulders. If Pluto had been the only thing out there and the rest of the Kuiper Belt didn't exist, then the whole question would have never come up. But the fact that it's part of a population, the vote was, if you're part of this population instead of being one of the big dominant members, then we're not going to call you a planet. So it's simply that. It's part of the population. No, that was an unfortunate misstatement in the very first AP report that came out that said because it crosses Neptune's orbit, it's automatically disqualified. Totally wrong, and just a misstatement by that particular reporter. It's because it's part of the Kuiper Belt, not crossing the orbit of Neptune.
Karen's,
the fact that it has the moon around it that's big, also unimportant. It's part of the Kuiper Belt. If you're part of the Kuiper Belt, you're not a planet. If you're part of the asteroid belt, you're not a planet. If you're part of any belt, you're not a planet. Black belts, brown belts, doesn't matter. No planets. Yeah.
Is there a plan or a possibility that New Horizon will take pictures of Eris?
It's unfortunately it would have to turn around and go the whole opposite direction, past the Earth again. Not quite as bad as that, but it's not in the right direction. New Horizons is actually trying very hard to go to a Kuiper Belt object. They don't. Actually, the bad news is Pluto. This is not a current picture. Pluto is about right here, or maybe more like right here, right these days. Pluto is right in the middle. Just bad luck. Pluto is right in the middle of the Milky Way galaxy, where Kuiper Belt objects are hard to find. So we currently don't know of any Kuiper Belt objects that are right on the path. It has to be very close to being. They don't have a lot of fuel to burn to make a sudden veering, so they have to go pretty much straight to Pluto and then go and a little bit off. We don't know of any objects right there right now, but I'm confident that people will find them. And I'm actually excited that they're going to go to Pluto, which is a large object in the Kuiper Belt, and then their goal is to go to a very small object. And I think you learn much more by going to a large one and a small one than by going to two really large ones that are going to be similar in some way. So I'm actually excited. Who cares if Pluto's a planet or not a planet, and what else? It's a very exciting mission, and I can't wait to see what those pictures of Pluto look like. You already asked one.
Would you expect Eris to have any methane reddening to keep it from being light so bright?
Absolutely. So if you take so Pluto is covered in methane in addition to having its nitrogen. A lot of things in the outer solar system is covered in methane. Titan, must be a picture of Titan somewhere in this room. We'll find pictures of something. There's no pictures of Titan anywhere in this room. Oh, there it is right there, the orange one. That's Titan. Orange because methane in the atmosphere of Titan, methane is carbon and 4 hydrogens, and if you take that carbon and 4 hydrogens and you do anything to it, you'll rip off one of the hydrogens, and then you'll start to build together these carbons, and you get the technical term for it is gunk. And gunk turns out to be red. You'll get this goo, this sludge, and that's what's going on there on Titan. Same thing should be happening on Kuiper Belt objects. It happens on Pluto. You see the red stuff on Pluto, absolutely. And if you look at Eris, Eris is not nearly as red as Pluto is. It's got a little bit of red to it, but not nearly as much. I think what's going on is it takes some time for this reddening to happen, and I think if you were to get out your razor blade and scrape off the surface of the atmosphere that's on the top, I think you would see the reddening underneath it. And I think that's why it's a little red, and you see a little bit of it in a few places, but it's not nearly as red as Pluto or some of these other things that are red out there. Yeah?
How do you know if Eris is round?
No idea. Might not be round. Most things out there are so big that they're probably round. The only way that Eris could not be round would be as if it's spinning pretty fast. It's so massive that no reasonable material could withstand the pressures and not come into a round shape unless it was spinning very rapidly. You know, the Earth is not round. The Earth has has love handles because it's spinning a little bit, but it still counts. We know that it's not. If it is rotating, though, if it is rotating fast and therefore not round, it has to be. We have to be looking at it almost precisely pole on like this, because what we don't see, if it's like this, we see it get brighter and darker and brighter and darker. Even if it's like this, we see it get brighter and darker. So it could be like this. From those images from the Hubble Space Telescope, we tried as hard as we could to see if we could detect any sort of elongation to it. And we didn't detect any. I think chances are it's not rapidly rotating, and in fact it is. We have other reasons to think that too. Actually, now let me think about this for a second. Here's a good one. We now know the plane of the moon's orbit. So assuming that it's rotating in the same plane that the moon is orbiting, just like the Earth is essentially, the Earth has a north pole and the moon goes around it, essentially the same place. Assuming that's also true for this, you're looking at it about an angle like this. So if it was rapidly rotating, you would see it do this. So that's how we know. Hadn't thought about that, but that's the answer. Now I know the answer. Okay, I have to go pick up my daughter from her babysitter, so I can only take one more question. Yes?
Is there a good reason to believe that there's an object about the size of Mars far away from the sun?
It's what, in the field we call hand waving. And, there was enough hand waving there that we could have probably flown across the room. It is a fairly inescapable conclusion that something large is out there. The size of Mars doesn't have to be the size of Mars. Maybe it's the size of Mercury, maybe it's half the size of Mercury, maybe it's the size of the Earth. But simply by one detection of Sedna, you can follow that chain and say one Sedna means 60 other things, maybe 30, maybe 90. If there are 60 things that are 3/4 the size of Pluto, the largest one is going to be the size of Mars, maybe Mercury, maybe Earth. And so the actual size of the largest one is extremely uncertain, but there are going to be many large objects out in that region that will be found over the next 5-10 years, so stay tuned. And I really can't take any more questions because I have to go get my daughter.